Hello. Okay, now in the next step we try to evaluate these three constants a, b and u0. Okay. Now first we start by evaluating a. So if you remember that f u, that is the distribution function, that is nothing but the number of particles per unit volume of the phase space. Okay. So if we integrate this one on velocity space, then finally we will have real space density. That means integrated over velocity space will simply give us the number of particles per unit volume in direct space, right. Then you can write the number density n should be equal to integration over f u, or rather here we just write f 0 for every distribution function, because we are talking about equilibrium now. Okay. This. Okay. Now we just have found that f 0 should have this form a e to the power minus b u minus u 0 whole square d cube u. Okay. And you can all the three, so this is a triple integral, okay, and all the components, okay, of u you have. So I can just write explicitly u x, u y and u z, you have the same limit minus infinity to plus infinity, right. Okay. And finally you can see that all, so this one can be written to the minus b u x minus u 0 x square plus u y minus u 0 y square plus u z minus u 0 z square. Okay. And these are the summation in the index. So they are nothing but making a product of three terms, and all these three terms, so if you write, that will give like this e to the minus b u x minus u 0 x whole square d u x times e to the minus b u y minus u 0 y square d u y, and the same thing for z component. Okay. And here you can easily understand that all these integrations are evaluated from minus infinity to plus infinity must have the same value, because they are just changing the variables. Okay. The functional form are exactly the same. Okay. So I can write a, this integration I call I. So a I cube should be equal to n. Okay. Now what is this and how to calculate this type of thing? So one can show that if you have an integration like this e to the minus alpha x square dx, that will simply be root over pi by alpha. This I leave for you as an exercise, okay, to calculate this. This is a very nice home task, okay, you can do that. And if you just substitute this one over here, you can see that this will simply be, so this one will have then equal to this one root over pi by b. Okay. So finally that will be a by b 3 by 2. Okay. Okay. if you have this result, then you can say n will be equal to a times pi by b 3 by 2. So, a will simply be n times b by pi 3 by 2. Okay. So, we find a relation between a and b, but still one characteristic variable of the system comes into play, that is the number density n. Okay. But still we cannot evaluate a and b independently of each other in terms of the other variables characterizing the system. Okay. Now, for that we have to use our concept of kinetic theory and to know the kinetic definition of pressure. Okay. And for that, so how to calculate, I just write this. Now, we have to calculate B. Okay. So, for example, if we can calculate B, then of course, we can also calculate E. Okay. And for that we have to first calculate, for that we start by calculating the pressure exerted by the molecules. Okay. Now, how really finally calculating the pressure could give us the value of B, you will just see. Okay. Now, let us take a cubic box. Let us take a cubic box, and in this box we are considering the particles are moving in every possible direction. Okay. And sometimes they are colliding with each other, sometimes they are just moving freely. Okay. And finally, when they are just moving without any collision, when I am talking about the freely, that does not say that they are not moving under any force, freely means without any collision. Okay. So, finally, when these particles are not experiencing any collision with any other particles, finally they are actually colliding to the walls of the container. Okay. This is also possible. For example, one particle is starting from here and it is going towards this direction, for example. Okay. And if it is not suffering any collision in this direction, then it will collide to this wall. Okay. The same thing can be happening for the other directions. Okay. Now, let us assume one cylinder of molecules. You see, this is the typical technique. Okay. One cylinder of molecules having velocity x component of velocity ux, and the cylinder is moving towards the positive x direction. So, we will be calculating the pressure given by the gas molecules on this wall of the container, and the momentum change. So, the pressure is nothing but the change of momentum due to the collision with the wall per unit time per unit area. Okay. Because momentum change per unit time is nothing but the force, and force per unit area gives you the pressure. Okay. Now, if you really understand what it means, this cylinder. So, the cylinder we are taking such that the cross sectional area which is perpendicular to the motion of the particles, okay, we call that delta A. Okay. And we are also taking the particles inside this cylinder are all having their x component of velocity as ux. So, in this direction, in this along the x direction and more precisely along the positive x direction, in unit time we can see a cylinder of u times or rather u x times delta t length. Okay. And this is the length of the cylinder, okay, which basically will be evolved, okay, in time delta t with the particles having velocities x component is equal to u x, okay, and moving along the positive x direction. So, when I am just multiplying this with delta A, that gives me the volume of this cylinder, and volume to this of the cylinder when gets multiplied to the number of particles, okay, which I just write as n of u x inside this cylinder, that gives me the total number of particle contained inside this cylinder. Now, every such particle, okay, every such particle, so for example, the particles which were here, okay, so the total number of particle will be this one, okay, number of particle in the cylinder. Okay. Now, every such particle will collide to the wall, and when it just before the collision it had a velocity component u x, and after the collision you had a velocity component minus u x, that we all know. So, the change in momentum, delta momentum, will simply be equal to mu x minus mu x. We are only considering the momentum change along the x direction. We are not considering any, I mean the momentum change in the other directions. Okay. So, they can have any other momentum change in y and z directions, maybe 0, maybe non-zero, but we are now considering what happens in the x direction. So, in the x direction they will have a momentum change of 2 m u x. Okay. So, the momentum change, okay, during a time delta t and with a cross sectional area of flow delta A, okay, will simply be then the total change in momentum, okay, that was for one particle. Total change is momentum will simply be 2 m u x times n u x del t del A. Okay. So, the pressure will now be this thing divided by delta t delta A. The pressure due to the particles having velocity, having x component of velocity is equal to u x will be equal to 2 m u x square. Okay. Now, so considering all possible, okay, so considering here we do not restrict the other component of velocities. Okay. So, considering all components so considering all possible velocities along positive x direction, and what is that all possible velocities? That means the range should be 0 to positive infinity. Okay. We finally have our P to be equal to 2m integration ux is equal to 0 to infinity, uy is equal to minus infinity to infinity, uz is equal to minus infinity to infinity, f ux uy uz, okay, ux whole square, okay, dux duy and duz. Okay. So, this part is giving me the pressure, but this is not an arbitrary pressure, this pressure is given on this wall. And if you do this integration correctly, you will see the total integration can be. So, now you can see that it will have 0 to infinity minus infinity to plus infinity minus infinity to plus infinity. Just remember, this is on ux, this is on ux, this is on uy, this is on uz, okay, and you will have to evaluate this u0x whole square ux whole square dux over there will be another term e minus b u I minus u 0 y square d u y, okay. And same thing for uz, okay. Then there one we should have a, okay. Now, finally, this is exactly equal to 2 m a, you have this integration 0 to infinity u minus b ux minus u 0 x whole square ux square dux times 2 integration square. And what are those integrations? They are the integrations over uy and uz. They are the same thing and they should look like integration minus infinity to infinity e to the power minus b uy minus u0y whole square duy, and also the same thing for uz, okay. And both of them should be equal to root over pi by b. So, I square I0 square will simply be equal to pi by b, okay, I0 whole square, okay. Then finally, we have this 2 m a pi by b 0 to infinity e to the minus b ux minus u0 x whole square ux square dux, okay. Now, you can actually try to evaluate this integration, this is not very integrate and evaluate. Now, one thing is that you have to do, so you can just make u0 x to be equal to 0 and that will make our life simple and we can easily evaluate the integration, okay. And what is the physical justification for that? That is, if you calculate the mean velocity, that means this one, and you can just say that my mean velocity will simply be given by this definition, that is I have the distribution function as a in the velocity space, okay, which is of course my equilibrium distribution function, okay, and the average velocity should be just u times the distribution function integrated over in the velocity space by the density, that means it is done to normalize this. So, it will be simply phi d cube u. Okay. If you calculate this integration, you will see that this will simply be equal to u 0. Okay. That simply gives you that physical significance of u 0. So, u 0 is nothing but the average velocity of the whole system. Okay. So, let us say if we have a container of gas, then the velocity with which the center of mass of the system will move will be equal to u 0. Now, let us put this constraint so that the u 0 is equal to 0. We make u 0 by hand is equal to 0. For this type of system, you can calculate the pressure, which will be equal to 2 m a pi by b integration 0 to infinity to the power minus b u x square dux. Okay. And by using some techniques of gamma integration, you can easily say this will be equal to m a pi root pi by 2 b to the power 5 by 2. Okay. Now, for this type of integration, I will give you a cheat sheet by which you can learn how to evaluate this type of integration. Okay. Now, we know from our knowledge of kinetic theory, this is equal to n times Boltzmann constant times the kinetic temperature of the system. N is the number density once again, right. So, finally, we can say this is equal to n kBT. Okay. And finally, if we remember what A was, so you can easily say this is now equal to, I am writing this part again in black, so that you can understand what is going on. This is equal to, so that was our previous knowledge that I insert over here, and that is now here I will have this. Okay. That will be m by 2 pi root pi b by pi 3 by 2 n, that is A, times 1 by b to the 5 by 2. Okay. If you do this simplification, you can see you have a very elegant result. B is equal to m by 2 kBT. Okay. And if you have B is equal to m by 2 kBT, then you have B is expressed in terms of the property of the system exclusively. Okay. Now, of course, here additionally we have introduced the temperature of the system. Okay. Now, A will simply then be n m by 2 pi kBT to the 3 by 2. Okay. Now, finally, inserting all these things, we have the final form of f 0, which should look like n times m by 2 pi kBT to the 3 by 2 e to the minus m u square by 2 kBT. Okay. So, this is the standard form of Maxwellian distribution. Now, remember, this is a function of u vector. That means, when I write this one and then u square is equal to u x square plus u y square plus u z square. Okay. So, there is a priori no assumption of isotropy. So, there is no assumption of isotropy a priori. Okay. Now, let us say we are trying to understand how should this distribution function should look like for a system where we have isotropy in terms of velocities. Okay. Then you can actually say that f0 u d cube u will then be equal to f0 u. Now, this d cube u, which is in general dux, duy, duz, will then simply be equal to 4 pi u square du. Okay. And that is exactly the isotropic form of f0, which we then call f of u scalar u, or rather f0 of scalar u, which will be nothing but 4 pi n m by 2 pi k b t to the power 3 by 2 u square e to the minus m u square by 2 k b t. Okay. So, this is the isotropic form of Maxwellian distribution, where we are just depending or we are just deriving a distribution function of the speed u. And what is u? U is nothing but modulus of the vector u, right. Okay. So, here I end this part. In the next part we will start deriving the deriving the evolution equation of different moments of velocities. Okay. Thank you.